Welcome to the Mathematics 23 review slides by the UP Mathematics Club. In these slides, we'll be discussing triple integrals in spherical coordinates. Let's begin by discussing what spherical coordinates are. So spherical coordinates are represented by these three coordinates, rho, theta, and phi. So let's say we have a point in R3. So the distance from the origin to that point, that's our rho. As for theta, it's similar to the theta of cylindrical coordinates, where if we project this onto the xy plane, this angle over here from the positive x-axis is our theta. Finally, our phi is this angle from the positive z-axis to the vector connecting the origin to our point. So that's rho, theta, and phi. So now that we've done a quick overview of what the spherical coordinate system is, let's go into some problems. So for problem 1, we need to use spherical coordinates to set up this iterated triple integral equal to the volume of the solid enclosed by the cylinder x squared plus y squared equals 9, and the hemisphere z is equal to the square root of 18 minus x squared minus y squared. So before I go into the solution, I'll let you guys think about this problem and maybe solve it. Okay, so for problems like this, I like to draw the solid before I proceed in the actual solving so that I understand what the solid looks like. So let's say we have our coordinate system. So first we have this cylinder, x squared plus y squared equals 9. You'll notice that this is just the equation of a circle in 2 dimensions. So if we bring it to 3 dimensions, it just becomes a circular cylinder. So the easiest way to draw that is to draw a circle in R2. And then draw another circle above it. And simply connect. So that's our circular cylinder. But what about this hemisphere? Well, a hemisphere is just a half sphere. But wait, how do we divide the sphere in half? Well, here you can see that z is equal to positive square root. So we just take the part of the sphere that is over the xy plane. So if I can draw it, it would look something like this. Then we extend that there. Something like that. That's what our hemisphere would look like. But the only important part to us is this part over here that intersects with the cylinder, the part over it. If I were to draw that in 2 dimensions, it would look something like this. This is the hemisphere. And this is our cylinder. So you can see that the hemisphere is on top and then it's cut by the cylinder. So this is our surface. And to make it even more clear, I'll show you guys a graph. So here we're using GeoGebra's 3D plotter. So as you can see, here's the hemisphere, and then there's the circular cylinder. So if we orient it if we project it sideways, you'll see that we need this shape over here. The one that's surrounded by the cylinder and the hemisphere. Okay, so now we know what our solid looks like. So how do we go about actually integrating it or setting up the triple integral? So let's let G be that solid from earlier. So in this case, we'll have to divide the solid into 2 parts, G1 and G2, where this first part is bounded by a cone in the hemisphere and the second part is bounded by a cone in the cylinder. But you'll notice that there was no cone mentioned in the given. So why is there a cone here? It will make much more sense if I show it to you. So let's move to the graph that we made. So we have this, and then we have to somehow construct a cone to divide this into two parts. And that cone will be this thing. Because if we rotate this, then it will become a cone. So why do we have to do this? Well, it's actually because if you look at rho, on this part of the cone, the hemisphere part, the upper bound of rho is the hemisphere. But on this, on the side of our surface, the upper bound is the cylinder. So basically, the two parts of our solid have two different upper bounds for rho. This one has the hemisphere, this one has the cylinder. That's why we have to divide it into two parts. One for the hemisphere, one for the cylinder. And this cone is how we do it. So we have to now proceed by finding the bounds for rho, theta, and phi for both G1 and G2. So the next step in this slide is to project G1 onto the XZ plane and to get phi. So let me show you guys how that would work. So let's say we have G. And then this light blue is G1. And let's let, oh wait. And let's let this red be G2. So what we do is project it onto the XZ plane. So now that we've projected our solid onto the XZ plane, we need to find this value of phi for G1. But how do we do that? Well, let's note that projecting on the XZ plane basically means that we set y equals 0. So if we look at the equations of our cylinder and our hemisphere, we should be able to get the coordinates of this point right here. And then if we construct this right triangle, we can use our trigonometric functions to find the value of this angle phi based on the coordinates of this point. So let's do that. So we have to note that this point is exactly on our cylinder. So our cylinder is x squared plus y squared equals 9, right? But if we set y equals 0, we just get x squared equals 9. Or in other words, x is equal to plus minus 3. Now, there's two answers here. Minus 3 would be what would happen if we took phi on the other side. But since we're taking phi on the positive x-axis, we'll take positive 3. So we know that this is 3 and then the z-coordinate. We don't know what the z-coordinate is yet. However, we can find it by using the equation of the hemisphere because now we know x. So we have z is equal to the square root of 18 minus x squared minus y squared, but y squared is 0 because y is 0. So we just zero it out. Now we can just substitute x equals 3, and then we get z is equal to the square root of 18 minus 9, or z is just the square root of 9, which is 3. So we know this point is 3, 3. And then, so in other words, this length is 3, and this length is also 3. So this is the opposite to phi, and this is the adjacent. So katawa, we have tangent of phi is equal to 3 over 3 is equal to 1. And if you go back to the slides, we'll see that if tangent of phi is equal to 1, phi must be equal to pi over 4. So that's our boundary for phi. So that may have seemed difficult, but phi was actually the most difficult to solve. So let's go back to this drawing. So now we have phi goes from 0 to pi over 4. So, but what about rho and theta? Well, theta is very easy because our surfaces have no theta dependence. So basically, you can rotate them using theta and they won't change. Theta is just the whole thing, or 0 to 2 pi. And 0 to 2 pi also holds for G2. But what about rho? Well, rho is somewhat easy if we look at this diagram. So when we integrate, we start with the origin. And since the origin is included in G1, rho has to start from 0. But what's the upper bound? Well, the upper bound, as we mentioned earlier, is just this hemisphere, which has the equation z is equal to square root of 18 minus x squared minus y squared. So again, if you rearrange this, we get x squared plus y squared plus z squared equals 18. But if we recall our spherical coordinate identities, x squared plus y squared plus z squared is just rho squared is equal to 18. So our hemisphere is basically rho is equal to 3 square root of 2. So that means that the upper bound of rho is 3 square root of 2. So these are our boundaries. So this reaffirms it. So we just have to write this integral g1 of dv. And then since all of our boundaries are constants, we don't need to worry about the order. And then just remember that dv in spherical coordinates is rho squared sine theta d rho d theta d phi. So now let's look for G2's bounds. So we already know the theta bounds. So we'll start by solving for phi, and then we'll do rho. Again, the theta bounds are 0 to 2 pi. It's like that for the whole solid, G1 and G2. Okay, so let's move to G2 here. So let's note that we already know that this is pi over 4. However, if we use this projection, we can see that there's a geometric way to find the boundaries. So let's note that G1 and G2 are basically connected here along this blue line. I'll circle it. They're connected here. That means that the upper bound of phi for G1 is the lower bound of phi for G2. So our phi runs from pi over 4 to something. But what is that something? Well, since the x-axis and the z-axis are coordinate axes, they're perpendicular. So their intersection forms this right angle. So that means that if you were to rotate from positive z all the way to positive x, you would have a 90 degrees rotation. Or in other words, you would have a pi over 2 rotation. So the angle over here on this end is phi is equal to pi over 2. So our lower bound is pi over 4, and we know that we go all the way to pi over 2. So that right there, that's the simplest way for me to explain why the bounds for our phi are pi over 4 and pi over 2. But what about rho? Well, rho is similar. We noted when we first drew this surface, or this projection of the surface, that the upper bound for rho was this cylinder. However, we're given the cylinder in Cartesian coordinates. X squared plus y squared is equal to 9. So what we have to do is convert this into spherical. So we just have to remember what x is equal to in spherical. X is just equal to rho cosine theta sine phi, and then y is equal to rho sine theta sine phi. So if we square both of these and then add them, you can check that we'll get x squared plus y squared is equal to rho squared sine squared phi. Let me just rewrite that. Rho squared sine squared phi. And then we can just write this as equal to 9. So if you want to get our rho value, we just divide both sides by sine squared. So we get rho squared is equal to 9 over sine squared phi. And if we take the square root of both sides, we'll get rho is equal to 3 over sine phi, which we can just write as 3 cosecant phi. So our rho just goes from 0 to 3 cosecant phi. And then as mentioned before, our theta is just 0 to 2 pi. So now we know all the boundaries of our G2. And if we check the slides, and then this is the way I just showed right now to solve for rho. So now we have our rho, phi, and theta boundaries, which we can then put here. Note that this time, the upper rho boundary is not a constant. This is not a constant. So we can't do it in any order. We have to do this one first. We have to do d rho first, and then we can put d theta and d phi in any order we choose. So our final answer is to simply add our integrals for G2 and G1 over here. And that will give us the volume of the entire surface G. So let's move on to problem 2. Problem 2 is another setup. So we have to set up the iterated triple integral in spherical coordinates, but we are already given a triple integral in Cartesian coordinates. So part of the challenge here will be to find out what this surface looks like without any description, just from these boundaries. And then the other part of the challenge will be transforming that surface into spherical coordinates. So again, I'll pause a bit to give you guys some time to think about this. So let's go into the solution. So first, we define some variables. So let's let m equal this iterated triple integral. You can think of it like m is mass, and then this is some sort of density function, if that makes it clear. And then g is the solid that we are enclosing with these boundaries. So we first have to write out what these boundaries are. So we note that z is in between this upper bound, square root of 16 minus x squared minus y squared, and this lower bound, x squared plus y squared over 6. And then similar things can be said for y and x. So we can graph the entire thing just from this information. But it would be easier for us if we start with a 2D projection, or the xy. Let's note that this is a type xy integral. So it's a projection onto the xy plane. But how do we graph this projection just by knowing the boundaries? So let me try to show you guys how. So let's note that the lower bound of y is 0. Or in other words, the x-axis is the lower bound of our y. So this line itself is the lower bound. It's the lower bound. Meanwhile, the upper bound is this square root of 4 minus x squared. So the upper bound is y equals square root of 4 minus x squared. But what is this equation? Well, it's actually the equation for a circle. If we square both sides, we can get y squared is equal to 4 minus x squared. And finally, we'll get x squared plus y squared equals 4. But similar to our hemisphere earlier, we note that y is only positive. I mean, we only take the upper half of the circle that this creates. So this is our upper boundary. But what about the x boundaries? Well, it goes from -2 to 2. So where exactly is that? Well, you'll note that if we substitute x equals -2 into this equation over here, we get y is equal to 0. So it's pretty simple that this is x equals -2, x equals -2, and this is x equals 2. Okay, so my drawing may not be very clear, but thankfully we have a graph. So again, this upper bound that I've encircled is y is equal to the square root of 4 minus x squared. The lower bound that I've encircled is y equals 0. And then, but we are bounded by x equals -2, x equals -2, and x equals 2. So this is our xy projection. So from this graph, we know that theta is from 0 to pi. So now we've found our theta values, but is there anything else we can determine from this projection? Not really. So in order to gain a better understanding of what our solid is, we must start graphing. So as you'll see here, our upper bound for z is this square root, and our lower bound for z is this x squared plus y squared over 6. So we'll note that if we set z equals to the square root of 16 minus x squared plus y squared, this is just a hemisphere. We saw this earlier, except this was 18. For the other thing, x squared plus y squared over 6 equals z, this was introduced in Math 22. It's a paraboloid. You can check that it's a paraboloid. If we set y equals 0, we get a parabola. And if we set x equals 0, we also get a parabola. So to get more information about the surface, we have to graph or draw the surface. Fortunately for you guys, I will just graph this surface. Okay, so we have our surface right here. So the upper bound is our hemisphere. So let me draw that. This is our upper bound. And this is our lower bound. So if we use spherical coordinates, we want to integrate from the origin, right? But yet again, we run into the same problem that we did in problem 1, where this upper bound has different raw values compared to the lower bound. So again, we'll use our favorite construction, the cone, in order to solve this problem. So we'll construct this cone, and then we'll divide our original integral into two parts. This upper part, which we again probably call g1, and then this lower part, which is g2. So now we have our clear idea of how to solve this problem. Yeah, again, g1 and g2, where we have a cone. So to solve for the bounds of phi, we'll do the same thing that we did earlier. So let me draw our surface, the projection of our surface. So we have a hemispherical top, and then a paraboloid bottom. This is a pretty weird surface. Let's just assume that that is a paraboloid, a parabola shape. Then we project it onto the xz plane, for example. So this is our projection. So yet again, we'll construct part of this cone, and then we have to find the coordinates of this point over here. So how do we go about this? Well, we have the equation for our hemisphere and our paraboloid. And we know that this point occurs at their intersection. So we just have to get what the intersection, or the intersection, that's a typo, what the intersection of the paraboloid and the hemisphere is. And then find the z value for that point. So I'll show it right here. So we simply manipulate both equations so that they're equal to 0. So for example, in the first equation, we multiply both sides by 6, then transpose 6z to get x squared plus y squared minus 6z equals 0. And in the second equation, we square both sides and transpose the right-hand side to the left-hand side. So we get this, which when we simplify becomes this, and we get z plus 8 times z minus 2 equals 0. But z cannot be negative because we're above the xy plane. So z must equal 2. So now we know that this point over here has coordinates something 2. And then we can just use one of the equations that we have in order to solve for the corresponding x coordinate in the xz projection. That is when y is equal to 0. So the easiest would probably be this first equation. So we get 2 is equal to x squared over 6. Or in other words, x squared is equal to 12 and x is equal to 2 square root of 3. So this is 2 square root of 3, 2. And then we just do a similar process where we construct a right triangle, phi, and then we take the inverse tangent. And I'll show that right here on the slide. Opposite over adjacent, tangent phi is equal to square root of 3, which means that phi must be pi over 3. So for our upper part of the solid, phi is in between 0 to pi over 3. Rho, on the other hand, is between 0 and 4. It's a similar argument for it's similar to the previous problem. Again, these problems are very, very similar, because you'll note that this hemisphere in red is the upper boundary for rho, and x squared, and this hemisphere has a radius of square root of 16, or 4. So its equation is just rho over 4. In order to show that more directly, you can just square both sides, transpose negative x squared minus y squared, and then you'll get rho squared is equal to 16. So that's our rho boundary, and we already know our theta boundary from earlier. So now we can move on to G2. So for G2, using the same trick that we did earlier, so we have phi is in between pi over 3 to pi over 2. Let me show the drawing again. So this is pi over 3. So the rest of this is just pi over 3. So the rest of this rotation is just pi over 3 to pi over 2, which is the positive x-axis in this case. So we know our phi boundary, we know our theta boundary. So what about the rho boundary? So to find the bounds for rho, we note that rho runs from the pole to the paraboloid. So the upper bound is just a paraboloid. But we don't know what the equation of a paraboloid is in spherical coordinates. So we still have to solve for it. So if we multiply both sides of this equation over here by 6, we'll get this equation. And let's just note that as we solved earlier, x squared plus y squared is rho squared sine squared phi. And z is just rho cosine phi. So it's important to know the identities of your spherical coordinates in order to solve these kinds of problems. So then we get this. So if we divide both sides by rho sine squared phi, we get rho is equal to 6 cosecant phi cotangent phi. Basically, cosecant is 1 over sine, right? And cotangent is cosine over sine. So if we divide both sides by sine squared, you get 1 over sine, and then you still have an extra over sine. But we already have a cosine. So cosine over sine is cotangent. That's how we got cosecant cotangent. And the 6 is just there. So now we know our rho boundaries. But we're not yet done. Unlike the previous example where we just had to plug in the boundaries and then substitute dv, we do have a density function or an integrand. So we also have to convert our integrand into spherical coordinates. They didn't show it here, but I'll go through it quickly. So we have z square root of x squared plus y squared. From earlier, we have z is equal to rho cosine phi. And then x squared plus y squared is just rho squared sine squared phi from earlier. So if we take the square root of rho squared sine squared phi, we just get rho sine phi. So this is our integrand in spherical form. This is that. And then this is just our dv, or dx, dy, dz. So both of our problems involve splitting our solid using a cone because it had different raw boundaries. Not every problem will be like this, but it's an important trick to keep in mind.